Hey everyone, this is Group 8, and this is our chemical and low thrust propulsion trajectories for long-term Pluto and Kuiper belt missions. I'm Mason Chin.
I'm James Hall Pryor.
I'm Mark Paz.
I'm Joshua Sullivan.
I'm Amir Far.
Here is our outline for tonight's presentation, breaking it down by the different sections that we'll be covering. To begin with, we'll discuss the mission background, then transition into the analysis background, and then into the mission overview, where we discuss the three different missions that we took, the modeling and assumptions, the technical calculations and assumptions, and then finally finishing with a summary.
All right. So for the mission background, in 2015, the New Horizons spacecraft flew past Pluto and revealed that Pluto is a much more complex world than previously thought. Nitrogen on the surface of the dwarf planet appears to vaporize and freeze in a manner similar to that of water on the surface of Earth. Irradiation of gas particles also creates organic molecules called tholins that create a haze and give the surface of Pluto its signature dark red patches. It's also thought that trans-Neptunian objects like Pluto and Kuiper belt objects were created by a series of collisions with smaller bodies, as demonstrated by the numerous craters and fractures in Pluto's surface. Studying trans-Neptunian objects and Kuiper belt objects could help scientists to further understand the formation and dynamics of objects in far reaches of the solar system. And then for our analysis background, in planning this trajectory, our team used Lambert transfers and a Earth to Jupiter to Pluto gravity assist trajectory. We developed pork chop plots via Easy Pork Chop in order to determine the time of flight and launch date, and then Free Flyer and Malta were used to create visual models of the trajectory. Hand calculations were used to determine the impulse and to verify the models that were found through the use of computer programs. And development of the mission also compared chemical propulsion and nuclear electric propulsion, as well as a spiral in versus a single impulse to Pluto capture for a nuclear electric propulsion engine.
Here's our mission overview. Our prime mission for our trajectory is to capture into Pluto orbit and potentially conduct a post-Pluto extended mission to fly by 2014 JR-80, a Kuiper belt object. Our launch window must be between 2029 and 2035, and our prime mission must take no more than 20 years. Our spacecraft's capture orbit must not drop below 100 kilometers altitude for safety. Our spacecraft will have a 2,500 kilogram dry mass and a characteristic energy of less than 150 kilometers squared per second squared to stay within the limits of NASA's Space Launch System. We'll be considering two trajectory types for this mission, chemical and nuclear electric propulsion trajectories. The chemical propulsion trajectory involves a gravity assist to Pluto, and after this, our spacecraft will perform an impulsive circularization burn into a circular orbit around Pluto. The two NEP trajectories also have a Jupiter gravity assist, but one trajectory circularizes around Pluto with a one impulse burn, and one trajectory circularizes with a spiral in maneuver. Next slide, please. Going over our modeling and assumptions, we assume that all trajectories will use a Earth, Jupiter, Pluto trajectory and model the timeline using Easy Pork Chop plot. We also allowed 500 kilograms of remaining fuel at the end of all our missions to allow for potential extended missions to Kuiper belt objects. Our spacecraft is going to capture into a 10,000 kilometer circular orbit around Pluto, allowing close surface studies. For our chemical propulsion trajectory, we modeled the Lambert transfer using Free Flyer and calculated delta V's and propellant mass using hand calculations. We have chosen our chemical propulsion method to be the Aerojet RL-10B2 liquid hydrogen liquid oxygen rocket engine, which has high thrust but low specific impulse relative to our nuclear electric propulsion method, which was modeled through Malta. Our nuclear electric propulsion method is the NEXC Xeon ion engine, which has a high specific impulse but a very low thrust. This engine will be powered by a 10 kilowatt Krusty nuclear reactor. As you can see, these two methods juxtapose each other. Next slide, please. Pork chop plots for our trajectories were modeled by Easy Pork Chop using the method of V-infinity matching. We found that the best departure time for our mission is right at the start of our 6-year window, January 1st, 2029. Our total time of flight on this timeline ranges from 7,188 to 7,213 days, falling within our 20-year prime mission time.
To begin the technical analysis of this mission, we will start by calculating the delta V's our spacecraft will perform. The first delta V burn that will occur will be for escaping Earth's sphere of influence. Using a parking orbit of 2,000 kilometers, we calculated a delta V burn of 7.43 kilometers per second. Next slide. The next delta V we calculate is the delta V provided by the Jupiter gravity assist. This can be found by first calculating the turn angle our spacecraft will be performing from our trajectory. We found that our delta V from the gravity assist is 12.89 kilometers per second. Our final delta V our spacecraft will perform will be for the Pluto capture for an altitude of 10,000 kilometers for a circular orbit. We found that delta V burn was 7.44 kilometers per second. Next slide, please. The next technical analysis we will perform will be our Earth to Jupiter heliocentric transfer orbit. To begin, we will first need to correct all of our orbital elements to our departure Julian day, and we can get that from our porkchop plot. Next slide. Since this is a non-Hohmann transfer trajectory, we will be using the Lambert problem approach. Since the mission is an interplanetary, we will begin with a geocentric equatorial coordinate system, and we will transform into a heliocentric coordinates. Once the planetary orbital elements are corrected from the previous slide, we will be able to find the angular momentum, argument of perihelion, mean anomaly, and the eccentric anomaly. But for the eccentric anomaly, we will have to do an iteration with a error tolerance set at 10 to the negative fifth, and we will have to keep comparing it until our ratio is smaller than that to ensure that it is within that tolerance. Next slide. Once we have our eccentric anomaly, we can then translate it over to the true anomaly. Once we calculated these new elements, we can find the position vectors R and V for each planet. The most important thing on this slide will be the heliocentric or the geocentric equatorial coordinate system to the heliocentric coordinate system, and you can see at the bottom that transformation is performed via matrix. Next slide. After obtaining the heliocentric position and velocity state vectors for both planets, this will allow us to calculate orbital elements for the heliocentric transfer orbit itself. This can be done by first actually finding the Lagrange coefficients and plugging them into the equations shown below to find the departure velocity and the arrival velocity. Next slide. Once we obtain those velocities, we can then actually find the orbital elements for our trajectory itself, and we can plug all those previous equations into the equations you see below. Next slide.
All right. For a mission that utilizes a chemical propulsion system, we found the following trajectories. So the mission would leave Earth on January 1st, 2029, and arrive at Jupiter on August 29th, 2030, for a total of 606 days spent in flight. The spacecraft would then spend the next 6,614 days in flight and arrive at Pluto on October 1st, 2048. The delta V's applied at each major orbital event are listed on the screen and were calculated in previous slides. The mission would require a total of 74,664 kilograms of propellant, and it would spend a total of 7,220 days in orbit or in flight for 19.77 years.
For the spiral in maneuver, from Earth to Jupiter, it takes 590 days and uses 15 kilograms of fuel. And the departing C3 is 105.3 kilometers squared per second squared. For the flyby of Jupiter, the V infinity is 10.82 kilometers per second, but that could be increased if we decrease the maximum flyby altitude. After the flyby, it is now on its way to Pluto and starts to spiral in on October 1st, 2048, and that spiral lasts a week. The spiral takes 8 kilograms of fuel, and the total propellant mass for the mission is 4,172 kilograms. And the total mission span is 7,220 days or 19.77 years. Next slide, please. For the one impulse, for this trajectory, the dates are very similar to the spiral in for the departure of Earth and the arrival of Jupiter and Pluto. However, although those dates are close, it does reduce the total mission time of flight by a week because it does not have to do the spiral in maneuver. Also because of the lack of the spiral maneuver, it saves about 75 kilograms worth of fuel. And if I were a project manager and had to choose a low thrust arrival to Pluto, I would choose the one impulse maneuver because of the previous factors stated. Also, for the auxiliary mission to 2014 JR80, a one impulse from Pluto will be used. Next slide.
So our auxiliary mission was chosen via our calculations and such. And the prime candidate that we chose for a flyby in the Kuiper Belt was 2014 JR80. 2014 JR80 is a Plutino planet-like orbit object orbiting around the sun in the Kuiper Belt, and it has a trans-Neptunian object, meaning that for every 2 rotations around the sun it does, Neptune will complete 3 rotations around the sun. It was discovered in 2013 by Pan-STARRS in the Haleakala area of the Kuiper Belt. It has a rough diameter of 454 kilometers, and the orbital elements of it can be seen at the bottom. As stated before by James, we will be using a 1 impulse maneuver following the 100-day observation period at Pluto. Leaving Earth, our spacecraft will have a C3 of 128.8 kilometers squared per second squared and roughly 2,500 kilograms of fuel. And then when the spacecraft will reach Pluto, it will have roughly 847 kilograms of fuel remaining, which will be more than enough to complete the impulsive maneuver to fly by 2014 JR80. Our spacecraft will reach Pluto in roughly 19 and a half years, and following the 100-day observation period it completes at Pluto, our spacecraft will then travel for another 4.5 years into the Kuiper Belt to find 2014 JR80, making our total mission time roughly 24.13 years, which is over the designated time, but this is due to venturing out into the Kuiper Belt to do this auxiliary mission. As seen, the NEP will be used to conduct this maneuver due to its high fuel efficiency, and the spacecraft mass will remain. The spacecraft mass will be initially higher than other missions, and which will allow us to venture farther into the Kuiper Belt. Next slide, please. And then finally, to summarize our findings, this is a compliance matrix in which we kind of analyze the different document sections and the different objectives that were given to us. Going down, you can see that with each step or each requirement that was given to us, all of them, we reached compliance in all sections, and we were able to verify each of these findings via 3 different ways, either using Malto, Free Flyer, or hand calculations. And each of the requirements was successfully able to be reached with none exceeding anything. The only areas in which we were close was our characteristic velocity for our auxiliary mission was close to 150 at 128, but still was not exceeding. So all requirements were successfully met. Next slide, please. And that's it, I think. Thank you for listening, and good night.